Hi and welcome to our presentation on forecasting atmospheric CO₂ concentrations, a time series analysis of Mauna Observatory data from 2010 to 2025. This project was prepared by Zain Abbas, Kaivalya Pulekar and Hrishika Kaur Arora. Our goal was to build a robust model to forecast atmospheric CO₂ levels using SARIMA methodology. Coming on to descriptive analysis, the dataset consists of monthly CO₂ concentration readings from 2010 to 2025, which is a subset of the original data dating back to 1958. There are 776 observations in total. From visual inspection, we observe a clear upward trend indicating that CO₂ levels are steadily increasing. We also detect strong seasonality with a repeating annual cycle. The variance appears stable over time, and overall the series displays non-stationary behavior, making it a candidate for time series decomposition and SARIMA modeling. Now with modeling approach, the trend modeling was necessary due to the non-stationary nature of the data. This was confirmed by the ACF plot, which shows a slow decay in autocorrelations. However, trend modeling alone was not sufficient. It doesn't capture autocorrelation, which are clearly present in the data. Therefore, we opted for a SARIMA model, which allows us to model both trend and seasonality in a single framework. For trend analysis, we started by considering linear plus seasonal model for which the adjusted R-square was 1, suggesting overfitting, and even though the harmonic model had an insignificant coefficient, we considered linear plus harmonic, which gave a slightly better adjusted R-square with one insignificant coefficient. We explored SARIMA modeling using residual-based approach and selected SARIMA 305-011 as the overall best fitting model. Using additional tools like EACF and BIC, we got some additional set of models that would be a good fit. Now coming on to parameter estimation, in trend analysis we mostly had significant coefficient in this model. We estimated the model coefficients using maximum likelihood and conditional sum of squares methods. The majority of coefficients in most of the models were statistically significant, suggesting that our selected models capture the key dependencies in the time series. The estimated parameters align with the expected autoregressive and moving average patterns. We have also captured goodness of fit metric like AIC, BIC, and 7 types of error estimates to check the best model in terms of efficiency. Coming on to residual analysis, we validated the model by analyzing its residuals. Talking about our trend model, the residual plot shows slight seasonality, and ACF plot shows that some autocorrelation and seasonal pattern still remains in residuals. As seen in the diagnostic plots, standardized residuals fluctuate randomly around 0. The ACF of residuals shows no significant lags. The residual histogram depicts normality, and the LB test p-values remain above the 0.05 threshold, indicating no autocorrelation. These results confirm that the residuals behave like white noise, suggesting our model is well specified. Now, in conclusion, the Mauna Loa CO₂ data from 2010 to 2025 exhibits a clear trend and seasonality. These characteristics made it ideal for modeling using SARIMA, which we applied after careful diagnostic and specification analysis. The final model SARIMA 305-011 passed all statistical checks and is well suited for forecasting future CO₂ levels. This work contributes towards better understanding climate trends, and such models can inform both scientific research and environmental policy planning. Thank you, and with this we will move on ahead with the reporting of the forecasting.